Okay, so good morning or good afternoon for everybody. So welcome to the fourth and last section of LSFA. We have two technical papers in this session, and the first one is going to be by a video. So Enrico in the video is going to talk about generalized abstract data types. So please, Alejandro.
Hello, I am Enrico Ghiorzi, and I am presenting the paper GADTs, Functoriality, Parametricity, Peak 2, written with Patricia, Johann and Daniel Jeffries. In this paper, we showed that the model for GADTs represented via fixed point of functors is not parametric. We also note that the fixed point representation of GADTs fails to be semantically equivalent to the interpretation of the church encoding. Data types can be thought of as containers for data elements. As a container, a data type has a shape determined by its type constructors. Data elements of a homogeneous type are arranged at the various positions within this shape. The type of list is the quintessential example of algebraic data type. Its two constructors, nil and cons, determine that, within lists, data elements are arranged linearly. As another example, a binary tree contains data elements arranged in the shape of, tautologically, a binary tree. Notice that an ADT's data constructors only involve the instance of the ADT being defined, so that different instances, for example, the type of list of integers and the type of list of booleans, are effectively defined independently. Nonetheless, since the shape of a data type is independent from the type of data it contains, we can define such data types polymorphically. Indeed, in the above definitions, the type arguments of the defined types are implicitly universally quantified. Since we adopt the point of view that data types are containers, we expect data types to be functorial. What that means that every algebraic data type has a functorial map which acts on the contained data elements without changing the shape of the container. Conversely, a natural transformation modifies the shape of a container without changing the contained data. Critically, functorial map and natural transformations commute. For example, given a binary tree and a function on its data elements, it is the same to first flatten the tree into a list and then map the data elements contained in the obtained list, or to first map the data elements contained in the starting tree and then flatten the obtained tree into a list. Algebraic data types can be considered as fixed points of functors. For example, the type of lists is the fixed point of the functor determined by the constructors for list, where the summand 1 is associated to the nil constructor and the summand A times list A is associated to the cons constructor. Being a fixed point, list satisfies the associated fixed point equation. Similarly, the type of binary trees is the fixed point of the functor determined by the constructors for tree, where the summand A is associated to the leaf constructor and the summand x times A times x is associated to the node constructor. Being a fixed point, tree satisfies the associated fixed point equation. By taking the fixed point of a higher order functor, which is a functor itself, we can abstract the type arguments and obtain a data type constructor, which is functorial in its type arguments. Thus, such type constructor has an associated functorial map, as defined in the previous slide. As an alternative to the fixed point representation, in a pure lambda calculus, we can represent data types by their church encoding. For example, we have a church encoding for a type of list where the term B is associated to the nil constructor and the term A arrow B is associated to the const constructor. By abstracting over the type argument, we also get a church encoding for the type constructor list. Similarly, we can represent the type of perfect trees via its church encoding, where the term A arrow B is associated to the leaf constructor and the term B arrow A arrow B is associated to the node constructor. By abstracting over the type argument, we also get a church encoding for the type constructor tree. Generalized algebraic data types are an extension of algebraic data types. Their constructors, indeed, can involve instances of the data type other than the one being defined. In other words, with GADTs, one defines a whole inductive family of types, whereas for algebraic data types, one defines a family of inductive types. Here we have three examples of generalized algebraic data types. The type of equality, which can only be constructed when its two type arguments are the same. The type of perfect trees, which is guaranteed to hold a power of 2 number of data elements thanks to the p-node constructor. And finally, the type of sequences, whose pair constructor exclusively forms sequences of pairs. We look at the church encoding for GADTs first, because the fixed point representation for GADTs is more involved. The church encoding for a GADT is possible within a higher kind of calculus. It is important to note that the church encoding for such a type comprises only those elements specified by the GADT's syntax. Next, we have examples of the church encoding for the types of equality and of sequences. We notice that the church encoding for GADTs can make essential use of the church encoding for the equality type. That is the case for the type of sequences, as we can see in the term associated to the pair constructor, which contains the term equal D and B times C. As opposed to the church encoding, the fixed point representation of a GADT corresponds to the data type comprising all data elements in the functorial completion of the type's syntax. That is, it also includes all those elements produced by applying, potentially repeatedly, the functorial map to elements yielded directly by the constructors. Functorial completion requires the categorical notion of left-can extension. Given two functors with the same domain, f and k in the diagram, the left-can extension of f along k is given by the minimal choice of a functor closing the triangle and a natural transformation filling the triangle, lang k f and eta in the diagram. Minimal choice means that given other such functor and natural transformation, h and gamma, there will be a unique natural transformation, delta, making the natural transformations eta and gamma commute. this is a so-called universal property. Equivalently, the left-can extension is the unique apto-isomorphism functor such that there is a bijection between natural transformations to the composition of G and K and natural transformations from the left-can extension. Our calculus will then have a primitive Lang construct, the syntactic reflection of the semantic left-can extension. The universal property of the left-can extension allows rewriting the declaration of a GADT's constructors. For example, we can rewrite the equality and sequences data types as shown in the example by using the Lang construct in the raffle constructor of equal and in the pair constructor of seq. Thus, data types can be written as fixed points. We now show with a counterexample that the fixed point representation and the church encoding of GADTs are not semantically equivalent. Let's consider a GADT whose only constructor provides an element when the GADT's type parameter is instantiated as 1. Then, a semantic computation shows that the church encoding for this type is semantically equivalent to the equality of its type argument with 1. That is, G is interpreted as the singleton set when its type argument is interpreted as the singleton, and it is interpreted as the emptied set otherwise. We notice that the fixed point representation can be simplified by actually removing the fixed point operator, as the recursive variable bound by the operator does not appear in the body of the type. The left-can extension can be computed by a colimit formula as the quotient of a union. Specifically, the union is the union of copies of the singleton set indexed by the unique object of the category of sets elevated to the exponent 0, that is, the unique category having only one object and its identity morphism, and the global sections of the set interpreting the type argument, that is, functions from the singleton set to the argument set, corresponding to the elements of the argument set. The union is thus a set of triples of which only the middle entry is non-trivial, since it holds global sections of the set interpreting the type argument. Indeed, the first entry is the unique object of the category of sets elevated to the exponent 0, and the third entry is the unique element of the singleton set. The equivalence relation identifies two such triples when the identity on one makes their middle entries commute, equivalently when their middle entries denote the same element. Thus, the equivalence relation is an equality relation, and the left-can extension is, ultimately, isomorphic to the set interpreting the type argument. This is different from the interpretation of the church encoding, and thus, the two representations are not equivalent. We then ask whether the fixed point representation can support a parametric model. Parametricity is an essential property of the semantic interpretation. For example, it is necessary to prove so-called free theorems, which provide useful term manipulations and even compiler optimizations. A parametric model requires two interpretations for types: a set interpretation taking as input the sets interpreting the type arguments and producing the set interpreting the data type, and a relational interpretation taking as input the relations interpreting the type arguments and producing the relation interpreting the data type. The set and relational interpretations have to be such that the relational interpretation is over the set interpretation, in the sense that the domain and codomain of the relational interpretation are given by the set interpretation. For the model to be parametric, it has to satisfy the identity extension lemma, stating that the set and relational interpretations preserve equality relations. Moreover, terms are interpreted as families of functions taking as input the interpretations for their type and term arguments. Term interpretation has to satisfy the abstraction theorem, stating that the interpretation induces morphisms of relations between the relational interpretations of its input and output types. In other words, term interpretation has to preserve the relations on the interpretations of its type arguments. In a categorical model, the interpretation of each type is functorial in the type parameters, and the interpretation of each term is a natural transformation between the functors given by interpreting types. This means that the naturality property of natural transformations described before holds. For our model to be parametric, we need the relational interpretation of every type, including GADTs, to be over the set interpretation. We show that this is not the case by providing a concrete counterexample. Let's consider the relational interpretation of the type G from the previous slide. That is given by a Lefkan extension of functors or of relations. Consider now the total relation over 1 and 2. We expect the domain of the relational interpretation to be that given by the set interpretation, in this case 1. Using the fact that Lefkan extension preserves projections and using calculations analogous to the ones from the previous slide, we get that the domain of the relational interpretation actually has 2 elements instead of 1. The relational interpretation is thus not over the set interpretation, and the model is not parametric. Thank you for listening to my presentation.
Okay, thanks a lot, Enrico. So it seems that Enrico was not able to be today with us, but Daniel, one of the co-authors of this paper, is here for answering questions. So do we have questions from the audience? Well, in the meantime, when you type your questions, so you can type your questions in the chat, but also you can unmute yourself, as far as I know. So the first question that I have is that it seems, so by taking a look at your paper, so it seems that in your examples, there appear some hidden elements when you consider the map in the GADT. So I was wondering if this, these hidden terms that appear in the program, they are realistic or they're very rare or something that the programmer should be aware of.
Could you say the last part again, whether they're realistic or?
Realistic, so in the sense that the programmer should be aware of this kind of things. If I'm using these GADTs, so what should I expect if there are some these hidden elements in my types?
Right. So the functorial semantics of GADTs using Lefkan extensions, as you said, it adds these hidden or extra elements that are not given by simply using the constructors of the data type. They also involve
the syntax.
They also involve right. They're added in order to to make the data type functorial. So the functorial view of GADTs is really fundamentally different than the church encoding or the syntax only. We also call the church encoding representation syntax only because it only includes data elements given by the constructors. And so yeah, for people that are used to programming with GADTs, this really is quite different. And I'm not sure how exactly programming with these like left-hand extensions, how that would differ. I don't know. I guess it's kind of difficult to compare to the, if you're used to programming with GADTs in Haskell or something like that. It's difficult to compare because it really is a different data type at that point.
Okay, yeah, it's very, different from the standard was, at least that I know. So do you have some concrete examples? So I know the example of the sequence that you have there, which is GADT, but it's not nested and it's not ADT, right? So do you have some other example that let us know that, when should I use this kind of types in our programs?
Right, that's a good question. We don't really have any concrete examples of here is a program that is using a particular GADT as a GADT as a functor, like via left-hand extensions. So we don't have any particular examples in that sense. But one of the ideas of the paper is that GADTs maybe don't really generalize algebraic data types so much, because for algebraic data types and nested types, the functorial, the fixed point representation and the church encoding representation coincide. And then once you get to GADTs, you can either have church encodings and parametricity, or you can have functoriality, but that causes you to lose parametricity. And so you have these two representations coincide for nested types, but not for GADTs. And so something really, really strange is going on.
Okay. So taking advantage of the last thing that you say, so you say that probably GADTs, they are not really generalization of ADTs. So probably this is a very silly equation. So do you have sort of expressing this result showing that you cannot encode GADTs into nested ADTs or ADTs directly? So there is something like this, like any program that you write using GADT, you cannot do it in some good way using the normal ADTs.
We don't have a formal result about that. I guess that's not something we've considered directly, but GADTs can kind of simulate some of the expressivity of dependent types. Well, if you have the equality type, then you can kind of fake some dependent types. And as far as I know, that's not possible with ADTs and nested types. So there are certainly some things that you can do with GADTs that isn't possible with ADTs or nested types. But we haven't considered if there might be some way to encode them that way.
Okay, just one curiosity. So in Haskell, you don't have GADTs, right? Or do you?
Haskell has GADTs, but they just have the data elements given by their constructors. No left-hand extensions there.
Okay. Great. Do we have questions from the audience? Not yet. Let me no. Yeah, so I have a last one. In the paper, you say that in some cases for GADTs, you may have problems with pattern matching because when you apply the function, you change the shape, the structure of your term. So, but this can be problematic later in the program because I mean, when you write the program, then you may have kind of race condition that usually when you have a typed language and strong typed language, you don't have this kind of thing. So typed programs, they don't go wrong, as Milner say. So what kind of guarantees do we have when we use this kind of types? From the behavioral point of view, like your program doesn't go wrong.
Sorry, you mean with GADTs as opposed to ADTs and nested types? Like what kind of stronger guarantees can you get using GADTs?
No, it's stronger, but you mentioned that you can change the shape of the term, and then you have problems with pattern matching. You mentioned that in your paper, but this doesn't happen in ADT as far as I know, right? Or does it?
Right. So right. So with GADTs, as with the functorial semantics, it's there are these hidden elements or extra elements given by applying the map function, but that don't correspond to any constructors. And so it's not obvious, I guess, how pattern matching should work syntactically, and that's not a problem for ADTs because applying a map function to a data element given by constructors, yes, it preserves the constructors. So it's not obvious how pattern matching should work syntactically, but the mechanism should still be there semantically, because pattern matching corresponds semantically to the initial algebra given by taking the fixed point of a functor. And so we haven't worked out or looked at what that would correspond to syntactically, but we do have that initial algebra for our fixed points.
Okay, great. Questions from the audience? Oh, if we don't have more questions, so thanks again. You can clap using the the reaction icon in your